Okay, so off we go. Chapter 4. We're going to do pretty much all of Chapter 4 today. Today being the last actual lecture meeting, that's what we're left with. In my first class meeting of today, I actually didn't finish the examples that I wanted to be able to do, but I am going to y'all saw my email, but I'm going to make a recording where I'll talk about those examples. If we get to some of those examples, that'd be cool. I'm not expecting we will. We'll see. Again, I blame Labor Day. Okay, so here's 4.1 is actually really, really quick. It's just kind of an observation that in the same way that there is a single variable Taylor polynomial, there is also analogously a multivariable Taylor polynomial. And the way we make the connection is just to observe what actually defines a Taylor polynomial. Right? Why are we interested in Taylor polynomials? And in the single variable case, the way it looks is this right here. We want a polynomial. We want to find the unique polynomial of the appropriate degree that mimics the function in value at the point A, in derivative at the point A, in second derivative, third derivative, fourth derivative, etc., all the way out to, well, whatever the kth derivative is, again, at the point A. So it's really kind of an extension of the idea of a linear approximation. You'll notice these first two terms here make the linear approximation, right? Just literally, that's exactly the linear approximation, which mimics f in value and derivative. Taylor polynomial says let's mimic it in higher derivatives as well. Okay. So it's an exercise that y'all can do for yourselves to confirm that this polynomial right here is what actually does all of that. Okay. All right, so what's the multivariable version of this? Well, we're going to look for an appropriate degree polynomial that mimics our function f in value at a point A, in, I'm going to say, first derivatives at the point A. Now, here's where things get a little bit different. There isn't just one derivative. There's a bunch of partial derivatives, one for each of your input variables, and this is a multivariable function. So there'll be several, what you might call first-order requirements there on the derivative. And then likewise, there's several second-order derivatives that we want to agree, third-order, fourth-order, etc., up to and including, then finally, kth order partial derivatives. Again, all of which, there's bunches and bunches of these, depending on how many variables you have. Okay, so that's, you see a pretty straight rip-off of the idea of a Taylor polynomial. We're just going to mimic the function in values and derivatives. And consider that probably is going to be a good approximation of the function we're interested in. Now, what is the function that does this? And there is a complicated formula for the, in general, for the Taylor polynomial of degree k. I'm just going to show you the degree 2 Taylor polynomial. Everything else is it's kind of notation heavy, frankly. And we're not going to have any use in this class for Taylor polynomials above degree 2. But here it is. This is the degree 2 Taylor polynomial. And again, you're going to notice a couple of things immediately. For one thing, notice again, the first two terms make up the linear approximation, right? Just like they did in the single variable case. And so additional terms are just being used to mimic the function in the additional derivatives, in this case, second derivatives. So the second order term, now I am going to shrink out for just a second here, and whoopsie, there we go. Let's look at the second order term here and compare to, I guess we don't have a second order term, but you can plug in k equals 2. So you see there's a 1/2, just like there is. There's two factors of x minus a, right, just like there is in the second order term of single variable. Different, though, because these are not multiplied by each other. They're separated by a matrix. Matrices do weird things. There's a dot product. It's a weirder expression, right? But this is the nature of just how it works out. And by the way, easily checked. And I think this is a nice exercise. Check directly for yourself that this polynomial right here agrees with f in value in all of the first partials and in all of the second partials with, at the point A with the target function f. Okay. All right. Is everybody good? Okay, now let's talk about what this second order term is. For one thing, I have to tell you what this matrix is, and here's the formula for it. It's just a formula. But it's just made up of all of the second partials. And when you do this, when you check for yourself that this function agrees with f in the second order partials, you're going to see why we need these there. Okay. The other thing I want to point out about this is if you look at this term right here, it actually should be a familiar construction. Right? This is what we call a quadratic form. So flashbacks to Math219. Right? Quadratic forms is a bunch of stuff you can say about quadratic forms, and that's going to come up in a few minutes actually. But I just thought I'd make that observation. Okay. That's really all I need to tell you all about section 4.1. It's otherwise just examples and stuff you've already seen before, namely single variable Taylor polynomials. So moving on then to 4.2. Everybody all right? Okay. All right. Okay, so optimization. So you know what I can do? I can hit that button. There we go. Like that. There we go. Okay, so single variable optimization, again, y'all already know this. These three conditions right here, if you have a point that's in the interior, if the function is differentiable there, if the derivative is not 0, the function is in the process of increasing, and therefore there is absolutely no way that that is the maximizer of the function. So easy example, you look at that point right there, the function is literally in the process of increasing when you're at this point. This can't be the maximum. It keeps getting bigger. Right? So this is an easy way to eliminate candidates. Right? If I'm looking for a maximum or a minimum, if I'm looking for an extremum, right? Any one of these three conditions happens, isn't it? We eliminate it immediately. Here's the good news. Those three conditions are satisfied at most of the points in the domain. All of those points that I have in green there can't be the maximizer that we're looking for. Now I'm coloring it green because I think of green as being, calm. It's a worry-free kind of thing. And I consider this to be good news because the point is not that we didn't find what we're looking for. That's not the right way to think about it. The point is these are points where we know what's going on. I know something about that point. I can draw a conclusion. I have actual knowledge about these green points. The problem is that at some points these conditions fail. I have points that are not in the interior of my domain. There are points where the function is not differentiable. Right? That happens. Boundary points are not in the interior. Again, points that are not differentiable. There are some points where the derivative is not 0. In other words, there's points where the derivative is 0. Y'all okay? Okay. All right. Points where the derivative is 0. Now what happens in this scenario? If any one of these conditions fails, well, I can't conclude. I can't say that I know what's going on at that point. I can't eliminate those points as possible maximizers. My test just fails. I don't know what's going on there. Right? Now, it is true that the maximizers I'm looking for will be among these points where I don't know what's going on. But the point I'm trying to emphasize is that I don't know what's going on. Okay. All right. So, again, this is kind of bad news. It's not understanding things. Again, this happens at boundary points. It happens at points where the derivative is 0. It happens where the function's not differentiable. These are the points that I don't understand. So how are we going to find maximizers? Definitely not the green points. I guess I better look at the red points. So we give those a name. We call them critical points. And we take it from there. Hope that looks familiar, everybody. All right. So great news. Great news. It's practically an identical argument in the multivariable context. Practically the same. Appropriately different to the context, of course. So here is my initial elimination argument. If a point is in the interior, let's look at a point like this one right here. If a point's in the interior and if the function's differentiable there, that means I can make chapter 2 arguments about how to compute like directional derivatives and stuff. If the gradient is non-zero, well, the gradient's pointing in the direction where the function's increasing. So if these conditions are satisfied, this can't possibly be the maximizer that I'm looking for because the function's increasing. Now, in this case, it's just kind of looking at the graph, and if you let's infer that it's as it appears to be, right? It would appear that if you're kind of going away from the boundary, kind of into the further into the interior here, it would appear that the function is increasing there. But whatever the direction of the gradient is, the function is increasing. So definitely not my maximizer. So again, good news. Most of the points in the domain are going to satisfy all 3 of these conditions, and therefore I can eliminate from consideration almost the entire domain here, which is hard to fill in because there's so many points. It's just kind of a messy deal there. Sorry about that. So most of the points in the domain, not it. Okay. All right. So tragically, there are some points not in the interior, aka on the boundary, such as that point, which might conceivably be the maximizer I'm looking for. I can't eliminate it. Ditto this point. Now, it doesn't look like it's a maximizer, but you know what? I think that might be the minimizer I might be looking for. I can't eliminate it because it doesn't satisfy my conditions. Then, of course, there's a bunch of other points on the boundary. Can't eliminate any of those. There are points where the function fails to be differentiable, such as this point right here. Right? Whenever that happens, can't eliminate it. There are points where the gradient is not 0. In other words, points where the gradient is 0. Can't eliminate those either. So that's this point there, and this point there, and that point there. So again, there's a bunch of points I can't eliminate. I don't know what's going on at these points. Again, red, not because they might be what I'm looking for. That sounds good, right? No, red because these are points I don't understand. I don't know what's going on at those points. Okay. All right. So again, not happy about these. We'll give them a name. We'll call them critical points. We'll, deal with them later with techniques I have that we'll come up with later. Okay, real quick, a bunch of terminology. A little bit of terminology. In particular, these points here, we call those saddle points. To be fair, there are different kinds of saddles, and I think you might be amused to look up monkey saddle as a fun little shape. That is another possibility that would again fail these conditions, right? And there is no kind of single variable version of a monkey saddle. It's a very 3D only kind of, or 3D at least kind of a thing. To further encourage you to actually look up, do an image search for monkey saddle. Somebody put a little saddle on a dog and got a monkey onto the saddle. And it's pretty hilarious, right? So you'll find that if you scroll through there and look for that surface. Okay, so let's do one. Oh yeah, question.
On that far left point, not like the boundary.
Why
is the gradient 0 there?
Yeah, it's like a mountain pass. So it's a Pringle. right? You think about a Pringle. If I were to have a Pringle here, wish I had a Pringle here. There's the spot right in the middle of the Pringle.
Yeah.
It's actually level there.
Okay.
You see what I'm saying?
It's just a level spot.
Yeah, and it's just I can't call it a maximizer because the function's kind of getting bigger in this direction, but it's kind of getting smaller going the other way.
As it was flat, but it's still like curved.
Yeah, it's kind of curved down. They call it a saddle because it's curved downward where your legs need to hang off, right? But it kind of curves up in front and it kind of curves up in back so you don't fly off the horse. Right. Yeah. Is everybody all right? Okay. All right. Okay. So, example. Let's find the critical point. Oh, here we go. Find the critical points of this function right here. Again, we have three different conditions to check. We want to check first and see, are there any points that are on the boundary of the domain for this function? This function's defined everywhere. There is no boundary. Every point's in the interior. There are no boundary points. So we don't find any critical points in that sense. Yeah?
What would it look like if there was something on the boundary?
Yeah, that would be something kind of like this picture here. Where, here I have a kind of a weird surface, right? But it's defined only on some finite domain down here.
But like
right?
equation-wise, would it be like plus a constant? Or?
I would have to be explicit about it. Yeah. So I mean, it could be that there would be that the function would fail to be defined somewhere, or like maybe the function fails to be defined for points beyond a certain distance from the origin or something like that. Yeah. But typically, if there's a domain that isn't just all possible points, then I would need to explicitly write what that is. Yeah. Okay. All right. Let's see here. Okay, so yeah, none of those. Second question. Are there any points? Excuse me. Are there any points where this function fails to be differentiable? Well, this is a polynomial. Polynomials are differentiable everywhere. Okay. Alrighty. Let's see here. Okay, so again, no critical points from that condition either. And then our last one, we look to see, are there any points where the gradient's equal to 0? And this is a plug and chug. You can just straight up compute the gradient. There it is. Right? And then you set that equal to 0. That's the 0 vector, of course, so both coordinates need to be 0. And then you solve. And this is actually pretty easy to solve because this equation here immediately tells you both possible values of x. And this equation here immediately tells you what y is. Is that good? All right. So 2 critical points. Now, here's the thing. This example here, this is the sort of good news example where solving this system is actually really easy. Solving systems is not always easy, right? Sometimes the algebra is weird, and when the algebra is weird, you have to be careful and consider cases. Okay, so for example, let's suppose that you're setting the gradient equal to 0. Maybe you end up finding a system kind of like this. How would we solve this system? Okay, well, looking at this top equation, I can pretty easily conclude that x squared is equal to y squared, and here's where a lot of students mess up. A lot of students have either been explicitly told falsely or have been allowed to get away with it to conclude that that must mean that x is equal to y. I'm going to put a big question mark on that. Well, that's absolutely not true. It's importantly not true. Right? I mean, there's clearly 2 possibilities here. You can just, easy counterexample with numbers. Negative 3 squared is equal to positive 3 squared. But negative 3 is not equal to positive 3. So it's just blatantly patently false, right? What this actually tells us is that there are two possibilities. There's a great big or right there. It could be that x is equal to y, or just as well, it could be that x is negative y. And if you're going to solve this system fully, correctly, you do have to consider both cases, and you have to consider those cases separately from each other. Okay, so here's that process. Let's start with the first case, x equals y. We'll take that case and plug it into the second equation right here, which then becomes this. And now we can just solve for y. Nothing to it. Single variable. Y is going to be 0 or negative 1. Is that cool? Everybody happy with that? No. Once you know y, now what does that tell me about x? Well, if whatever y is, you can plug that into the condition, and that tells you x, and that then gives you your two critical points. Is everybody all right? Okay, now, of course, that's just one of the two cases. You can't just do just the one. You also have to consider the second case. The second case is x equals negative y. That's a completely different assumption that we're taking as we do the rest of the algebra. When you plug that in to this second equation, it makes this second equation turn into something very different. Right? And you get different corresponding values of y. And thus, when you take those values of y and plug them into the condition, and again, now this is, don't plug it in up there, right? We're not doing case 1 anymore, right? You plug it into case 2, and out comes 2 more critical points. All good? Okay. All right. Okie dokie.
So would the final answer to this be that there's 3 critical points?
Correct. So at a careless glance, it would look like there's 4, but of course these are the same. So yeah, that's correct. There are 3 critical points. Now, just as a reminder, the answer, y'all heard me say this a million times. It's not about the answer; it's about the reasoning, right? And so if the maximizer we were looking for happened to be one of the ones that I found, right? But I didn't find the other critical point. The reasoning is still incomplete. Even though the numerical answer is there, the reasoning is still applied. Okay. All right. And remember, grading is on the basis of reasoning, not results. Okay, so on to the second derivative test. Again, revisiting. Are y'all okay? Everybody fine? Okay. So again, revisiting. Here's the single variable second order Taylor polynomial. I think, by the way, there's a bunch of different ways that you can interpret the second derivative test single variable. This is one that I think is convenient for our purposes here. And specifically, I can consider points where the derivative is 0, and thus this term disappears. And at those points where the derivative is 0, the behavior of the function is pretty much entirely determined by this one term. And this one term, 1/2 is always positive. X minus a quantity squared is always positive, at least away from a itself. And so whether this expression is always positive, thus giving me a minimum, or always negative, thus giving me a maximum, is entirely determined by the value of the second derivative. Right, so that's an easy sort of foot in the door way to justify or to motivate or think about the second derivative test. Okay. All right, so we're going to do basically the same thing here for the multivariable second order Taylor polynomial. We'll consider at critical points where the derivative is equal to 0 and thus this term disappears. The behavior of this function is entirely determined by this term, namely this quadratic form. And y'all may recall, one of the big things you talk about when you look at quadratic forms is when is a quadratic form positive definite or negative definite or indefinite. And these correspond with these conclusions. If this matrix, and thus this quadratic form, if that's positive definite, this term's always positive, well, then it's uniquely bigger everywhere nearby your point, and you are looking at a minimum. That makes sense to everybody? All right, so bad news, good news. The bad news would appear to be that we might need to look at the rules for how to decide if a matrix is positive definite or negative definite. You may recall they're a little inconvenient to work with. It's not really super happy about. You got to find the eigenvalues and so here's the thing. There is a clever bit of linear algebra that you can do, and I'm going to say I encourage you to think this through, but you don't have to. You're not responsible for it. But there's some nice arguments that you can make in here that allow you a pretty simple punchline of for this specific case. Looking at a Hessian matrix, because it's symmetric, it works out really nicely. And here's the nice punchline. We don't even really have to think of this in terms of positive and negative definiteness. We can just look at the rules. Here we go. Step 1, look at the Hessian determinant. There's 3 possibilities. What you're hoping doesn't happen is that it equals 0, because if that's the case, then the test fails and you lose and you know nothing. That's unfortunate. There's another possibility. It could be that it's negative, in which case you have a saddle point, which is actually, I think, is a pretty nice conclusion. This is arguably the easiest way to get an actual conclusion. Just if that determinant ends up being negative, you have a saddle point. End of story. The other case, and fairly common occurrence, of course, is for that determinant to be positive. If the determinant's positive, then there is a next thing that you have to look at. You don't immediately get a conclusion from this determinant being positive. You then have to look at the actual value of the top left entry in that Hessian matrix, namely the XX second partial, and the nice conclusion looking at that XX second partial. This is actually a little bit familiar. This is kind of like the single variable second derivative test. Positive means a minimum, negative means a maximum. Okay, but you have to keep in mind, this business right here only applies if that Hessian determinant is positive. Okay. All right, so example, and I'm going to be quick with the example because it's literally plug and chug into the second derivative test rule here. And actually, I've got to keep that up on the page. Here we go. Let me clear this off. Right, so we have previously looked at this function. We found 2 critical points. We threw up our hands at the time and we're like, I don't know if these are maxes or mins or neither or what, right? I have no idea what's going on here. Here's how we can tell, at least in this case. I'm just going to follow the rules. And let's see here. Here we go. We will start with this first point. Plug it in to see what the Hessian determinant is, and it is negative, which means saddle. Again, that's kind of that's the dream scenario. That's what makes it the easiest to work out. So, handy. Okay. Looking at the second point here. This second point, plug into the Hessian determinant, and you get positive, which means we got to take it a step further. I have to look now and ask, okay, well, what's the value of fxx? Is that positive or negative? Well, again, you can just kind of look right. There's your fxx. Plug in the point in question. It is positive. And missed. Positive means min. So B is a local min. Yeah.
Why are we interested in like fxx versus fxy?
Yeah, that's there's a bunch of linear algebra that goes into that, and that's what I was kind of hoping that we could gloss over, sweep under the rug. I mean, it's really very cool linear algebra, and I encourage you to play the game, but it's a long discussion. Yeah. Okay, second derivative test. The nice thing about this, it's very pluggy-chuggy. Just follow the rule. It's totally an algorithm. Just do the algorithm. Okay, global extrema. Let's talk about this a little bit. There's a problem with our process of elimination. So keep in mind, that's what we're doing here, right? In fact, if I go back to the very first page here, second page. We have here a process of elimination. I eliminate all the green points where I know for sure that's not what I'm looking for. And then, what's left? I guess the maximizer must presumably be one of these remaining uneliminated points, right? So it's a process of elimination. And here's the problem with a process of elimination. Process of elimination only works if you know the thing you're trying to find actually exists, right? I mean, just as a silly example, let's suppose I wanted to identify who in this room has ever been to the moon, right? And if I ask everybody except for him, and nobody else has been to the moon, I guess you've been to the moon. Nonsense. Absolute nonsense, right? Process of elimination only works if you know the thing you're looking for exists. So how do we know that the maximizer that we're looking for exists? And there's a bunch of cases in which, say, maximizer simply doesn't exist. Check this one out. The function keeps getting bigger and bigger as I move to the left. There is no maximum value. And so there is no point that achieves a maximum value because there is no maximum value. So this is a wild goose chase. Don't try to find a maximizer there. There isn't one. Right? And likewise in these other cases. Right? So as it turns out, in a pretty significant sense, these are the only three things that can go wrong. If you're trying to find a maximizer, there's really only three ways that a maximizer can fail to exist. If your domain fails to be closed, if your domain interval is open on one end, if there's part of the boundary that's not actually included in the set, then this kind of nonsense can happen. If there is an issue with the domain not being bounded, if your domain extends infinitely in any direction, if you can't put your domain in a box, right, infinite in any sense, then, the function could just keep getting bigger and bigger and bigger and bigger as you go in that direction. It's another possibility. And another possibility, it could be that your function might fail to be continuous, as I sort of see here, right? So if your function fails to be continuous, then this kind of nonsense, you can have an asymptote right there in the middle of the domain. Nothing wrong with the domain at all there, right? But the function could just have an asymptote like this. Again, no maximizer. Okay, so if all three of these conditions are satisfied, then none of these kinds of problems can happen. And as it turns out, and this is not a rigorous argument, and we don't have time to fill in those blanks, it's not really natural for this course. These being, I'm going to say unrigorously, being the only possibilities, when these three conditions are satisfied, there is a global max and a global min somewhere. All right, so let's see here. We have 5 minutes left. Okay, so the next couple of pages here, we're going to be skipping. These next couple of pages are basically this is going to be the kind of argument that we're going to try to avoid. This is an inconvenient, tedious, and unnecessarily difficult option. So we're going to skip all this. If you want, just for kind of the spectacle of it all, if you want to wade through this stuff, you can. But there's a much easier way to answer this question. And specifically, what we're going to find a better solution for is how to check on the boundary. And remember, our methods so far do not address how to find critical points on the boundary, how to gain knowledge about what's happening at points that are on the boundary. Right? So what we're going to do instead is go to the good method. Here it is. It's called the method of Lagrange multipliers. This is going to allow us to deal with boundaries. In fact, it's going to allow us to deal with even more than that. This is going to allow us to address how to optimize some function, biggest possible value, smallest possible value, with the understanding that I'm only going to look at points that satisfy a certain constraint. So, easy example, here's a constraint. I'm only going to look at points where this equation is satisfied. And among just these points, I want to know what point is closest to the origin. And, of course, closest to the origin means I want to minimize distance, right? So you take away the constraint and ask just directly what point is closest to the origin. It's a super easy question. The origin is closest to the origin, right? That's super duper easy. But with the understanding you have to satisfy this constraint, that you're only interested in points that satisfy the constraint, this becomes a much harder problem. Does that make sense to everybody? Okay. All right, so there are going to end up being two functions that are involved when you have one of these constrained optimization problem. There's the function that you want to maximize or minimize. We call that the objective function. This is what we want to make as big as possible, as small as possible. And there's what we call the constraint function. The constraint function is the function whose level set, the function that has to equal to a constant, the function whose level set we have to be on. And what you're going to notice in this equation is conveniently here that was already written as a level set, and so I can read straight from this being a level set that this is my constraint function. Is everybody all right? Okay. So, a couple of examples, real world applications. I got ahead of myself there. Here's a reasonable question. What's the biggest box that you can make with a given amount of area, given amount of materials to make up the surface area, the outside area of the box? So it's a practical problem, but also this is a constrained, give me 2 seconds, constrained optimization because I want to make volume as big as possible, but I have a constraint that area has to be a fixed value. Yeah.
Sorry, in that previous example, the objective function, where did that come from?
Yeah, right. So I was trying to find the point that is closest to the origin. Closest to the origin means I want to make distance as small as possible. The point that makes distance as small as possible is also the point that's going to make distance squared as small as possible. Okay. And so, I mean, if you wanted to be sort of literal about this, you could put a square root on there, but you're going to get the same x and y independent of whether you have that square root there or not. Yeah. Okay. All right. Okay. Okay, so how do we do this? Again, we have a set of conditions that are going to be satisfied at most of the points in our domain. These conditions, when satisfied, will allow me to confidently conclude that those points are not the ones that we're looking for. So we, again, process of elimination, again, green because this is good news because I get to draw an actual conclusions about these any point that satisfies these conditions. I know something. Specifically, that's not what I'm looking for. Okay. So again, it's where these conditions fail, as I see here, it's where these conditions fail that the problem comes up. I mean, how do I find points where these conditions fail? How do I find points where the functions are not differentiable? Conveniently, that's usually a matter of a glance. How do I find points where the gradient is equal to 0? That's an algebra that you can just write down. And how do I find points that satisfy this equation right here? Again, that's just algebra that you can write down. And again, these points I can't eliminate because I don't know what's going on. We have to kind of accept that these might be what we're looking for. We don't know. We'll figure it out later. We call them critical points, and then we deal with it later. How are we doing? Is everybody with me? Sadly, I think I am out of time. This is pretty close to where I was going to leave off anyway. Notice that there are some examples here. I'm going to go through these examples in detail in some recordings. I'll send them to you as soon as I can. See you later. See you. Oh, don't forget, exam on Friday. Oh, and again, this material not fair game for the exam. Yeah, see ya.